Okay. Welcome everyone to today's extremal and probabilistic webinar. Our speaker today is Hao Huang from Emory, who will be talking on local Turán problems. And before I will pass the stage to Hao, just a few organizational things. Firstly, in case you have some question during the talk, please write it in the chat, and quite often it's gonna be answered already by some other participant before we even notice. But in case there will be some question that remains unanswered, I will tell Hao about it, and he can answer it himself. After the talk will be over, there's gonna be a question time, which is gonna be recorded like the whole talk itself. So if you don't wanna be recorded in any way, well, then don't ask questions during this time. But after that, we will also have some non-recorded chat sessions, so you can ask more informal or not or questions that you feel they should not be recorded during that time. Okay, so I guess maybe that's it for the beginning. So now okay, How it's your the whole e-board is yours.
Thanks, Jan, for the introduction. I would like to also thank the organizers for the invitation. So today I'm going to talk about some local Turán problems. So you probably can't tell much from the name, but I will define everything properly later. So this is based on joint work with Peter Franco and Berta Roto. I think everyone knows them pretty well. So during the talk, I should be able to monitor the chat window, but occasionally if I miss some questions, please, Jan, maybe please you can let me know. So every talk, one moment. Every talk about Turán problems, people always start with the 1907 result by Mentor, which says that if you have an n vertex graph, which contains no triangle, then it has at most n squared over 4 edges. So the tight example showing that you cannot do better than n squared over 4 is just by taking a complete bipartite graph, such that these two parts are almost equal sizes. So that n over 2 vertices on the left, n over 2 vertices on the right, and you connect all the edges between them. Now, if you have a triangle, then two vertices must belong to the same set, and this could not happen. Okay, so if you look at the complement of this graph, so you just get the union of two vertex disjunct copies of cliques. Okay, so there are many different ways to prove this mental theorem. So for example, you can just use the double counting argument plus Cauchy-Schwarz equality, or you can do an inductive proof, or you can apply some type of operations on the graph. And last year, there was a pretty interesting proof. So in that, you can just generalize this Hoffman bound to hypergraph. So they call it a higher dimensional Hoffman bound argument. And from there, you can prove mental theorem. But I guess the authors have difficulty showing the same result for K4. Okay, so now about K4. So in this seminal paper of Turán in 1947, he showed that if you have an n vertex graph which contains no cliques of size t, then it has at most this number of edges. So the example is again by taking a complete t-1 partite graphs. And if you look at the complement, so you just get the vertex disjunct unions of t-1 copies of cliques each of size n over t-1. And if you ignore all the lower order terms, then the edge density is just this 1 minus 1 over t minus 1, or 1 over t minus 1 in the complement. So for a lot of these Turán density problems, quite often we can't even determine the precise minimum or maximum densities. So that naturally leads to this definition of this Turán density pi of h. So if we denote by exn of h, the maximum number of edges in an n vertex graph without a copy of h, then if you divide this by the number of edges you see in so this should be n choose 2. for graph. So if you divide this by the actually, if you can define this for any hypergraph, then it becomes n to the v of h. So if you define this to be the minimum density, maximum density, and you take the limit where n goes to infinity, then this is the so-called Turán density of h. It's not so hard to use some averaging argument to show that the limit exists. All right, then it comes this another famous result by Erdős, Stone, and Simonovich. They showed that actually this Turán density for graph is determined just by the chromatic number of this graph. So it's 1 minus 1 over chromatic number minus 1. So for example, triangles have chromatic number 3. So just get 1 minus 1 over 2, which is 1/2. And the complete bipartite graph has edge density roughly half. And then if you try to do the same for hypergraph, you will find this is a pretty miserable problem. So you can't even solve the precise Turán density for the almost the simplest hypergraph, this K43. So here, whenever I use this notation, it means the complete 3 uniform hypergraph on 4 vertices. So it has exactly 4 edges. So there's a conjecture in the same paper by Turán, who asks, is it true that the Turán densities of the complete 3 uniform hypergraph on t vertices is equal to 1 minus 4 divided by t minus 1 squared? So let me briefly explain what this number is, when t is equal to 4. So here you get t equals 4, so it's 1 minus 4 over 9, so you get 5 over 9 here. And the example is actually very easy to show, but it's still open that this is the best construction. So just take the partition the vertices into 3 disjoint sets. Each contains roughly n over 3 vertices. And now you take all the triples containing 1 vertex from each set. And then you take the triple containing 2 vertices from the first set, 1 from the second, 2 vertices from the second, 1 from the third, and 2 from the second, 1 from the third, 1 from the first. So if you compute the density of this graph, when n goes to infinity, you get roughly 5 over 9. And on the other hand, you can easily show that this hypergraph does not contain a copy of K43. And so, okay, so this is upper bound. This is a lower bound. So for the upper bound, so there are various attempts trying to bring this number as close to 5 over 9 as possible. So far, the best result was done by Razborov using this so-called flat algebra method. So he showed that the Turán density of K43 is at most this number 0.56166666. So if you compare this with 5.9, so you can see this is 0.55555. So they're reasonably close, but there's still some gap between them. And I think people believe that this, well, at least quite some people believe that this flat algebra method can never lead to this tight bound. If you don't apply some further stability arguments. Okay. So let me summarize what this Turán density problems for complete hypergraphs actually says. So for example, if you look at the complete R uniform hypergraph on Q vertices, you want to find its Turán density. In other words, you want to find the maximum number of edges in an R uniform hypergraph H, such that it does not have a clique or hyperclique of size Q. So if you look at the complement of this hypergraph, so it's the same question of minimizing the number of edges of an R uniform hypergraph, such that this complement does not have an independent set of size Q, right? If you take the complement, then cliques becomes independent set, and dependent set becomes cliques. So if this hypergraph does not have an independent set of size Q, it's the same as saying that whenever you take Q vertices, then, so now assuming the uniformity is R, then all of them induce a hyperedge. So now we can ask a very natural generalization of this problem. So what happens if we replace this R by some other constant P? Okay. So this is a so-called local Turán problem we would like to consider. Okay, so let me say this again. So you have 3 parameters, Q, P, and R. So I think you need Q to be strictly greater than P, and P is greater or equal to R. Okay. So now you want to minimize the number of edges of an R uniform hypergraph such that no matter which Q vertices out of this R vertices, out of N vertices you take, then some P of them must induce a hyper edge. So what's the minimum number of edges or the minimum edge density here? So let's try to write everything in a formal way. So now, so we call this property QP if for every set of size Q, you can find a subset of size P that spans a clique. And again, let's denote this big T function as the minimum number of edges of a hypergraph satisfying this property. And just like in this Turán density definition, so you can look at the minimum edge density, and if you let the total number of vertices n goes to infinity, then the limit exists, and you denote this density as this little t of QP. So that again, 3 parameters here. R is the uniformity. Q is the number of vertices you take. P is the size of the hyperclique you would like to guarantee here. So here I'll stop for a moment. Is there any questions regarding the definition of this local Turán densities? Okay, so now let's see some special cases of it. So we just so before we talk about definitions, I kind of show why this is a natural generalization of the complete hypergraph Turán density problem. So basically, if you take P equals R, then this is exactly 1 minus the Turán density of the complete hypergraph on Q vertices. So now if you take R equals 2 in the graph case, then this number is 1 over Q minus 1, right? Because the Turán density here, this thing here is
sorry, how I'm still not sure I am passing the definition correctly. So this Y is something which you can then extend to an edge, or it's a P. So P is less than R, right?
P is greater than R. So Q is greater or equal to P. P is greater or equal to. So I think the first one has to be stripped. So no. P is like you have a set of vertices.
Okay.
At least R vertices, and you want every R tuple of them to form an edge.
Okay.
So it's a hyperclique of size. Okay, so let me say this. This is actually a hyperclique of size P. All right. So we know that for this pi kq2, it's just 1 minus 1 over q minus 1 from Turán's theorem. So for graphs. So this t function is just equal to 1 minus that. So it's 1 over q minus 1. That should be easy. And the example is just you take this q minus 1 copies of vertex cliques, each of size roughly n over q minus 1, and you let n goes to infinity. So you get this limiting density. Now, what happens if you still have the graphs, but you do it for arbitrary q and p? So it turns out that this is equal to 1 over this q minus 1 divided by p minus 1. I think you have to take the floor function. So again, if you set p equals 2 here, so you get exactly 1 over q minus 1 over q minus 1. Just in line in Turán's theorem. So I'm not going to discuss how this can be proved, but later I will show you why T2 of 2p plus 1, p plus 1 is equal to 1/2. You see, if you let q equals 2p plus 1, p equals p plus 1 here, you get exactly 1/2. Right? So I will show you the proof of that. And the general proof is actually very similar to that one. Okay, and finally, so if you take q to be sufficiently close to p, so we know that q has to be greater than p, right? So you see, for example, if you have a hypergraph which has property, let's say q plus 1p, then it means that for every set of size q plus 1, you can find a hyperclique of size p. Then of course, for every set of size, let's say q plus 2, then you can also find a hyperclique of size p inside, right? So if you increase this number, that is actually a weaker property. So in other words, if you want q to be very small, you should expect that this density to rise, probably, right? So when q is sufficiently close to p, actually you can show that you need this hypergraph to be almost like close to like 1 minus little over 1 proportion of the edges in the complete hypergraph to guarantee this property QP. Okay. All right, so let's go back to this Turán's conjecture for a moment. So we talk about the case K43, and we haven't really discussed why the conjecture is this 1 minus 4 over t minus 1 squared for general t. But if you take t equals 5, so you get what? 1 minus 4 over 16, so you get 3 over 4. So for the complementary problem, you should expect 1/4. Right? And the example there is also very easy to describe. So what you do is, one of the conjecture extremal example, right? I'm not talking about all of them. So you can just take n over 2 vertices here. So let me call this set x. And you take n over 2 vertices here, you call this set y. And now it's a 3 uniform hypergraph. You can take all the triples such that all of its vertices belong to the same set. Okay. So first, let's count how many edges we have. So you have n over 2 to 3 edges, n over 2 to 3 edges. So this is roughly 1/4 times n to 3. And now, why it does not contain a copy of, why the complement of it does not contain a copy of k by 3. Okay, so in other words, if you look at this phi 3 property, so I want to guarantee that for every 5 vertices, you can always find a clique of size 3. So, okay, so you use the pigeonhole principle. So if you pick 5 vertices, there are essentially only 3 cases. You have 5 in one set, 0 in the other set, or 4 in one set, 1 in the other set, and 3 or 2. So even in the worst case, you have 3 vertices belonging to the same set, and they should form a clique of size 3. Right. Okay, so now if you generalize this example to a I-uniform hypergraph, you can see essentially we can expect the same construction to work for the 2p plus 1p plus 1 property. So what you do is the same as before. So you just, instead of taking kn over 2 to 2, kn over 2 to 2, you do this kn over 2 to r, and then kn over 2 r for I-uniform hypergraph. Now, this hypergraph satisfy this 2p plus 1p plus 1 property by just again by pigeonhole principle. And the S density you can compute. This is equal to this 1 over 2 to the r minus 1. Okay, because you have S density, you have number of edges roughly 1 over 2 to the r in each set, and you have to multiply this by 2. Okay, so this gives us a very simple proposition. So for any p and r, this local Turán density is at most, when for this 2p plus 1, p plus 1 property is at most 1 over 2 to the r minus 1. Okay, so let me rephrase this in a different way. So basically there exists a I-uniform hypergraph with its S density roughly 1 over 2 to the r minus 1, such that satisfy this 2p plus 1, p plus 1 property. So any questions so far? All right, so now we know that this is like an upper bound, but of course we wonder whether there's a matching lower bound. So let's look at the graph case first. So if you remember this earlier result, which says that T2 QP is equal to 1 over Q minus 1 divided by P minus 1. So you have to take the floor function here. Then if you let Q equals 2P plus 1, P equals P plus 1 here, then you get exactly 1/2. But why is this greater or equal to 1/2? We only see this is less or equal to half, right? And the reason is very simple. So let's see what this actually means. So if we would like to show that this thing is greater or equal to 1/2. So it's same as saying that if this density is less than, let's say 1/2 minus some little o 1, then there exists 2p plus 1 vertices such that there's no hyperclique of size p plus 1. Okay, so that's something that we like to show. Okay, so let me call this hypergraph. Now it's a graph. Let's call this graph G. So now if you look at the complement of G, then G bar has density at least half plus little o 1, right? Because the complement the density of complement is just 1 minus the density of the original graph. Now from Turán's theorem, sorry, I think here you need this Stone-Simonovich. Then G bar contains a copy of 2p plus 1 cycle. That's because the quadratic number of any odd cycle is equal to 3. So its Turán density is equal to 1/2. Okay. So if your host graph has density greater than half, then it must contain a copy of that particular cycle. Okay, so now let's see what this cycle looks like. So it has 2p plus 1 vertices, but the independence number is bounded from above by p. Right? Okay, so now this basically shows you this sentence about it. So if the density in the original graph is less than half, then there exists 2p plus 1 vertices, so that they induce no clique of size p plus 1. So here we are only using the fact that all the odd cycle contains, like, let's say 2p plus 1 vertices, independence numbers at most p, and the Turán density is exactly 1/2. So if you agree that for the graph case, we always get this 1/2. So the next thing that you may wonder is what happens for the 3 uniform hypergraph case. So we know that for p equals 2, Turán's conjecture says that maybe this number is equal to 1/4. Well, it means that this T3 of 5/3 is equal to 1/4. That's this conjecture by Turán. And so maybe you can expect similar things to hold for larger p as well. So Franco in 1984 showed that the limit is actually equal to 1/4. So we cannot quite show that all these things are 1/4, but I can show that if your p is sufficiently large, then if a hypergraph satisfies this 2p plus 1, p plus 1 property, then its edge density is greater or equal to some number which might be slightly below 1/4, but the limit tends to 1/4. And the main result I'm going to present today, there are 2 results. And the first one says that, so basically you can generalize this to I uniform hypergraphs. So this TR 2p plus 1, p plus 1 also has a limit tending to 1/2 to the r minus 1. And actually you can replace this 2 by any integer a. So in other words, if you have an I uniform hypergraph such that every AP plus 1 vertices induces a clique of size at least, induces a sub-hypergraph whose clique number is at least p plus 1, then you need at least this many edges, and the limit of this minimum density is equal to 1/a to the r minus 1. So actually we can prove something slightly stronger. So we can change this AP plus 1, p plus 1 to APP. And the reason that this is slightly stronger is because this this AP plus 1, p plus 1 property implies this APP property. So you actually have this density, so first density here, to be greater or equal to the second density. So now you see the limit is also greater or equal to this one, but we know the upper bound is like 1/a to the r minus 1. You can just generalize the previous example. So instead of taking two vertex disjoint copies of hyperclique, you can just take a copies, right? So you get the density to be 1/a to the r minus 1. Okay, so basically we only need to prove this second statement. So I'll get to the proof later. But there's another quite surprising result saying that for the 3 uniform case, actually for every p greater or equal to 3, we get the exact density here to be 1/4. Okay, so let me say a few words about what this means. So when p is equal to 2, so this is a conjecture by Turán saying that this T3, phi 3 is equal to 1/4. So we don't know how to deal with this case, of course, otherwise we would have claimed this $500 reward by as earliest. Yeah, but for this local Turán property, we can show that for every p greater or equal to 3, this density is always equal to 1/4. So not only the limit in this case is 1/4, but for every value when p is greater or equal to 3, this is equal to 1/4. Okay. All right, so let me first spend some time talking about the idea of the first proof. So we'd like to show that if you consider this property AP plus 1, P plus 1, or actually I will show this case. If you would like to consider this property APP, then this limiting density is equal to 1 over A to the R minus 1. So here you can see even for R equals 2, and let's say A equals 2, this might not be equal to 1/4. Okay, but the limit is 1/4. So that's two different notions. So for example, if you let P equals 2, then this is exactly 1 minus the Turán density of the clique with 4 vertices. I mean, I'm talking about the 2 uniform case. And I think this is equal to 1/3. Okay. But the limit is equal to 1/4 in this case. All right, so before I talking about the proof, let me try to briefly sketch the idea of proving it. So to do that, I need to introduce a few notations. So here, this QP is the property that we are studying right now. So eventually, we would like to consider the property APP. So, okay, so now let's only focus on the property QP such that Q is less or equal to AP. That of course includes our case. And we define this function AP minus Q to be the excess of this pair. Okay. So to some extent, it will measure how strong or how weak this property is later. And if you have an I-uniform hypergraph on the vertex set Y, so a subset of its vertices Z is called a WV hole if Z contains W vertices. And if you look at the induced subgraph on this induced sub-hypergraph on this set Z, then the clique number is V. But most importantly, you want this induced subgraph to have relatively small clique number. So your V is strictly smaller than W over A. Okay. So in some sense, you can think of this like if you have a WV hole, you have a relatively locally sparse sub-hypergraph. So the first lemma we prove is the following. So if your F does not have this type of hole, which is pretty sparse, then your hypergraph F has to be locally pretty dense. So we showed that, okay, so if it doesn't contain all hole of size W less or equal to AL, so when we are talking about a hole, so here we assume that this W is strictly greater than A times B always. Okay. So you want this sub-hypergraph to be a hole if the clique number is sufficiently small compared to the number of vertices. So if that holds, then we actually know that for every subset of size A times L, F A times L is this bound on the number of vertices in this hole here. Then we know that for all the AL subset Y, if you look at the F induced on this subset of vertices, then it contains at least A times L choose R vertices. Okay, I don't plan to go through the details of this proof. It's just some induction plus some counting argument. But let me at least show you where this A times L choose R come from. So if you take the previous example, so you have this N over A vertices in each set. And you take an R edges inside. So it's this union of this Kn over A R. Okay. So first of all, this hypergraph does not have any WV hole. So if you take a subset of W vertices, then by pigeonhole principle, at least W over A vertices must belong to the same part. And these vertices will induce a hyperclique. Okay. So it means that this hypergraph, this particular construction does not contain any WV hole for any value of W. And now if you look at an AL set Y, okay, so basically you take an AL set Y here. Now you can do some optimization. and show that the minimum number of edges spanned by this subset of A times L vertices is at least this A L choose R. And this the minimum is achieved when every set has size exactly L. Okay. And that's essentially where this A L choose R, this number comes from. And for the proof, as I said, you need to do a little bit of induction. It's not that difficult. But we need to, let's assume that the size of this set is equal to S, and we have to do induction on S. Of course, it's difficult to do induction for this S divisible by A. Right? So you can actually prove a stronger statement, and then you use induction to prove this stronger statement. So I think what it looks like is the following. So if you have S equals A minus B times T plus B times T minus 1, T is basically what you get from, let's say, dividing S by T, okay? Then you have this F intersect Y choose R. So you are counting the number of edges induced by this subset Y. And this has to be at least A minus P, B times T choose R plus B, T minus 1 choose R. So that's the actual statement we prove in this induction. And then you just take the special case when S itself is divisible by A. Okay. All right. So what we just did is, if the hypergraph does not contain a WV hole, a relatively sparse hole, then the hypergraph has to be sufficiently dense locally. And now the second lemma kind of tells us why we define this excess and this WV hole here. So if you have a hypergraph G, which is R uniform, and it has this property QP. Okay. So if you take, let's say if G contains a WV hole, then you can actually remove those vertices in this hole. So you get an induced subgraph on the set Y minus Z. Then it has to satisfy property Q minus WP minus B. So I think that's quite obvious just from the definition of this WV hole. So for example, if it doesn't satisfy this property, then it means that you can find Q minus W vertices, and the clique number is really smaller than P minus B. Then you just take this set of Q minus W vertices together with the vertices of this WV hole. Then this will violate the property QP. All right, and the reason that we define this excess here is because if you have this WV hole, so again, here we need this W to be strictly smaller than, sorry, W is strictly greater than A times this clique number. So if that happens, then the excess actually increases by at least 1. Why is that? So, okay, so what's this new property? So it's Q minus W, P minus V. So the excess here is just, you have, just by definition, you have A times P minus V minus Q minus W. So right here, we are looking at this new property, Q minus W, P minus V. So to compute the excess here, so we need to do it not for P and Q, but for these new parameters. So here we get AP minus Q minus, let me just plus maybe plus W minus AB. So by our definition of this WV hole, W has to be greater than A times the clique number. Right? So this is greater or equal to 1. And this is actually the previous excess here for the QP property. So every step, if you cannot find a WV hole, then you know that the graph has to be locally pretty dense. So from there, you can get some lower bound on its S density. And on the other hand, if in this case, you can actually find a WV hole, you can pass to a sub-hypergraph, so this one here, which satisfy Q minus WP minus V property. And this property is in some sense stronger than the previous property because it has a larger excess here. And again, to see that this excess somehow defines how strong this property is because if you look at this AP minus Q, for example, if you fix Q, and if you sort of decreases, you fix P and you decreases Q. So when you have a larger excess here, so you actually have a stronger property. because you need fewer vertices to guarantee a hyperclick of size P. Okay. All right, and the remaining part is just to do all these formal proofs and to finish it. So let me, again, just say a few words about how this works, but I guess no one was very seriously look into this slides. So here we just assume that there are a few parameters. So A and R is just the things we need in the statement of the proof. So A is the basically the number of paths in this extremal construction, and R is the uniformity. So here we have an intermediate parameter L, which is much bigger than A and R. And then we take this P as in this APP property, this parameter P to be sufficiently large than this intermediate parameter L. And then of course, I mean, in every case, we let the number of vertices to be much larger than all these parameters. Okay, so we start with a hypergraph on the vertex set of size n, and satisfy the APP property. So let me call these two parameters Q1 and P1. Okay. So at the I step, if we can find a WIVI hole that is relatively small. Okay, so here there are two things we need. First, we need Wi to be greater than A times Vi. So you need this hole to be relatively locally sparse. And also you want to upper bound the number of vertices here. So if you can find a relatively small, this locally sparse hole here, then we can just delete these vertices and continue to the next step. So after I steps, if you cannot find any small WV hole, then by lemma 1, you have a hypergraph which is on the vertex set xi here. And it's locally dense from lemma 1. So the number of remaining edges has to be greater or equal to, so here I do some averaging argument. So from lemma 1, you might recall that if you take any AL vertices, they induce at least A times L choose R edges. So now just do this averaging argument. So if you have xi vertices left, then the number of remaining edges is at least this quantity here. And the nice thing is that if you let L to be sufficiently large, then the second term here tends to 1 over A to the power of R minus 1. That's basically what we want. And you just need to show that the first term is close to N choose R. And the reason it is close to N choose R is because your Xi cannot be too small. You only lose an epsilon proportion of vertices in this procedure. Okay. So here I don't plan to talk about how you do this, but basically you use this our restrictions on the values of Q and P in these steps, and then you get an inequality, and you can show that the number of remaining vertices is at least 1 minus little o 1 times n. So you end up with 1 minus little o 1 times 1 over A to the R minus 1 times N choose R edges. Okay, now this is the case that after a certain number of steps, you cannot find any small WV hole. Now what happens if you can always find this WV hole? So we like to show that this is not possible. And this is why we need this P to be sufficiently large compared to L. So okay, again, I don't want to go through too much of the proof, but basically we can use this, how we define this excess here, to show that every step you can upper bound this excess by n minus 1 times q plus n plus 1. And because in every step, this excess increases by at least 1, right? So so remember we start with the property with Q1 equals AP, P1 equals P. So the initial excess here is equal to 0. Okay, so this term is equal to 0. So after m steps, the excess is at least m. So from here, we can get upper bound on this, the number of steps you can possibly go to. And now for every step, you lose like W1 vertices and so on. So, but in every step, remember we take a whole which is relatively small, right? So you have this upper bound, like I think A times L on the number of vertices of this whole. So every time you lose this at most A times L vertices, And the number of rungs you have is bounded by this a minus 1 times qm plus 1. Again, this is smaller or equal to some 2 times a times l. Remember, we restrict so here we have this qm plus 1 is less than 2al. So if you do all these computations carefully, you can see that eventually you have this q1, which is a times p. This has to be less than 2aq times l squared. But if we take p to be sufficiently large in L, then this will never happen. You get a contradiction. And this is why here we cannot really solve for every values of p. You get exactly 1 over a to the r minus 1. But if you take the limit when p goes to infinity, then you get this, the correct limit. Okay. So for remaining part of this talk, let me briefly mention why for the 3 uniform hypergraph case, you always get 1/4. And actually, this proof itself is just by combining some previous results by other people about the Turán densities of certain 3 uniform hypergraphs. So, okay, so as I said, I cannot say anything about the case p equals 2, but let's start from p equals 3. So basically, the first case is T3 of 7, 4. So if a hypergraph has the property 7, 4, meaning that every 7 vertices induces a sub-hypergraph with clique number at least 4, then its edge density is at least roughly 1/4. Okay. So to show this lower bound, it suffices to consider the complement of it. And if you can find a 3 uniform hypergraph H on exactly this 2p plus 1, in this case is 7 vertices, and the independence number is less or equal to 3, and the Turán density is less or equal to 3/4, and we are done, right? Because if you look at the complement, if the edge density is greater than 3/4, they must contain a copy of this H. Then just like this odd cycle argument for the graph case. So in the original hypergraph, it contains some 7 vertices whose clique number is only at most 3. So to solve this 7-4 case, so we use the earlier result by Mubay and Rodo. So they define the so-called F minus 4, 3 hypergraph. So what you do is you have 4 vertices here, 1, 2, 3, 4. And you have 3 vertices, 5, 6, 7 here. So here you take all the triples formed by the first 4 vertices, and you almost take all the triples in this way, except 1, 5, 6. Okay, so once again, you take this K43 union IJK. So I is in this 1, 2, 3, and JK is in this 5, 6, 7. But you want this IJK to be not equal to 1, 5, 6. Okay. So if you take this hypergraph, so they can show that the Turán density is equal to 3/4 by a very beautiful counting argument. And now if you think for a moment, you will realize that this hypergraph has 7 vertices. Okay, so let me call this R. So the number of vertices is equal to 7, and its independence number is equal to 3. And the Turán density is exactly what we want. So, okay, so that basically shows you there exists such an example that gives you this 1/4 as a lower bound for the 7-4 property. So now the next case is this 9-5 property. Then you can expect what will happen. Right? We will find a 9 vertex uniform hypergraph whose independence number is at most 4, and the Turán density is at most 3/4. So here we have to rely on the result by Weber and Talbot in 2012. So they use this algebra method to find such a 6 vertex uniform hypergraph whose Turán density is equal to 3/4. But if you are paying attention, you will realize that we need a 9 vertex uniform hypergraph, right, with that Turán density. So what we do here is we can blow up the vertices of this 3 vertex hypergraph in the following way. So for 1, 2, and 3, we blow it up into 2 vertices each. And for 3, 5, 6, we just keep 1 copy. And whenever you see a triple, you just, let's say if you see a triple, let's say 1, I don't know, 1, 4, 5, for example, then you just make 2 copies, 1 prime 4, 5, and 1, 4, 5. Okay. So now we just obtain a 9-vertex hypergraph. And nice thing is that when you blow up, the Turán density never increased. So you get upper bound 3/4, and that's what we want, right? In the complement, we like to find a copy of this blow up. So that's 9 vertices, and you can show that the independence number is equal to 4. So what's the independence set here? So independence set must be roughly from the blow up of these edges that you cannot have in your original hypergraph, right? So now if you check this carefully, you can see that none of this will produce an independent set of size 5. And of course, they could be like you take maybe some 2 vertices, but then that gives you at most 4 new vertices in this blow-up. Okay, so we solve this for the 7-3 property, the 9-5 property, but what happens in general? And actually, you just take, I don't know how to make this edge connected, but you can just take the union of, let's say, this 7 vertex example R with a copy of K43. Then this solve the 11-5 case. And the reason of this is because, so you see this pi of R or pi of T has Turán density 3/4. Right? But the Turán density of the complete hypergraph or complete uniform hypergraph on 4 vertices. By Borlow's result, this is less or equal to 0.56 something, and this is strictly less than 3/4. So if you take the union of this, you still have this upper bound on the Turán density as 3/4. And every time you add 4 vertices and the independence number increases by 2, right? Because the independence number of this K43 is equal to 2. I mean, if you take 3 vertices, that already gives an edge. So you just need this P equals 3 and P equals 4 case to get all these examples for the remaining cases. Okay. So this basically says that, okay, so let me summarize it here. So it says that for the uniform case, if you like to find the minimum edge density for hypergraph satisfying this 2p plus 1, p plus 1 property, then this is exactly 1/4, minus little 1, of course, for every p greater or equal to 3. And for p equals 2, this is still open. And that's because this is the K53 problem. It's supposed to be very difficult. And for the uniform case, we can generalize Frankel's result and show that the limit is 1/2 to the r minus 1. And as I said, we can replace this 2 by a, and it's still correct. And finally, I would like to mention a conjecture here. So maybe if for any fixed uniformity R here, if you take this P to be sufficiently large, then the minimum edge density you need for this 2p plus 1, p plus 1 property is indeed equal to 1/2 to the r minus 1. So we know that this is true for r equals 2, right? And it's true for I equals 3. So we don't know the starting case when p equals 2, but we know it for every later p. But for p equals 4, of course, we cannot really rely on this, always rely on this flat algebra result. But maybe there's a nice way of explicitly construct some hypergraph with 2p plus 1 vertices. Independence number is strictly smaller than p plus 1 and has the Turán density we want here, okay, by some nice double counting argument. And the reason that, okay, so for I equals 2 and I equals 3, it's reasonable to expect that actually every value is equal to 1/2 to the r minus 1. I mean, of course, we don't know the K53 case yet. But we cannot expect the same to hold for every uniformity here. So for example, if R is equal to 4, for uniform hypergraph, if you consider the 7-4 property, so it's already not equal to 1/8. So in a recent paper by Sidorenko, he showed that there exists a construction that gives upper bound, which is roughly 0.08 something, which is less than 0.125. Okay. But maybe if you increase this p, you still get precisely 1/8 starting from certain p. I don't know. And now if you go back to the 2 uniform case, so we can actually have a pretty precise result, right? Because if you fix the length of this odd cycle to be 2p plus 1, then the Turán density, the Turán number of a 2p plus 1 cycle is equal to n squared over 4 if your n is sufficiently large. So I think here you don't really need n to be super large. Just it's good enough for n to be greater than some linear function in P, I guess. Okay, so if you go back to that proof, so not only it shows that the minimum Turán density for this 2p plus 1, p plus 1 property for graphs is equal to 1/2. But you can show that this minimum number of edges is equal to this sum here, which is like n choose 2 minus this n squared over 4. So now can the same hold for the 3 uniform case? So we know that for 3 uniform case, for every p greater or equal to 3, the minimum edge density is 1/4. And that comes from this example of taking 2 copies of 3 uniform clique on n over 2 vertices. But maybe that's indeed the best example, not just asymptotically, but precisely. We don't know. And finally, so we know that the limit for this t sub r of AP plus 1, p plus 1 is equal to 1 over a to the r minus 1. But we only dealt the case when this a are integers. So what happens if you replace this by gamma? So if you look at how we take this union of this several copies of K43 together with one small hypergraph, you can see maybe it makes sense to ask this for some other rational numbers gamma here. Okay, not just the integer values. Okay, so I think it's a good time to stop, and thanks for coming to this talk.
Okay, thank you, Hao, for a really nice talk. I ask everybody who is wishing to clap during the recorded part to unmute themselves and give a round of applause to Hao. And are there any questions?
Hao?
Hi, Victor. How are you?
Hi, doing well. And so, thanks for a lovely talk. I was really curious about your second question. So you left it very open. What can we say? So actually, what can you say? Like, do you have some constructions that show at least that it's different from, suppose you take gamma between a and a plus 1? Can you have a construction showing this, the answer should be at least separated from one of these two numbers?
So so your question is for gamma different from integer?
Yeah, so I guess you have some interesting construction that aren't take a bunch of cliques.
Right, so I mean, instead of taking a bunch of clicks, you can take a bunch of R's or a bunch of T's. So I think that should give you something about gamma.
Sorry, can you repeat that?
So okay, instead of taking R union a bunch of K43, you can take just the union of a bunch of R's. And this will make the independence number even lower, I guess. I mean, relative to the number of vertices. You see, because the number of vertices from R is equal to 5, and the independence number is equal to 2.
Yeah.
I think that says something about the case when alpha is equal to 2.5.
Okay, oh, that's an interesting one.
But I think if maybe the right answer for this is like comes from this K53 example, but since we don't know anything about that one, so yeah, I don't know.
And if no one else has can also ask about your first question. There's been a lot of work on stability result, the funnel plane. So the funnel plane has the same extremal construction. Mm-hmm. And now a lot of proofs that you can get the Turán number in this way. And have you looked at all at using those results to try to get?
You're saying that the funnel plane has Turán density 3/4, right?
Yeah.
But is the independence number equal to 3? Right.
No, I was more thinking of the fact that in this case we have the same extremal configuration, but a lot of people have basically said, once we can show that we've got stability, we've got some sort of machinery that allows us to get the Turán number.
Mm-hmm.
So
for funnel plane, I see you have the independence number equal to 4, right?
Yeah.
So Right. So we want to have I mean, for our proof to work, we need to have 7 vertex with hypergraph whose independent number is 3, and with that Turán density. So, right. I mean, probably you can use the idea to show if that.
Yeah. So I wasn't meaning the results, but just you had a question whether you can get the exact covering, like the basically due to the local Turán number, and.
Yeah, I mean that's possible. Actually, I think maybe at least for this case, 7-4. If you go into this proof by Mobile and Roto about the Turán density of that particular hypergraph, if you do it carefully, you should be able to show that this is precise.
Yeah, I think it's.
But I'm not sure about this Weber-Talbot result because that's done by algebra. So unless you can do it slightly different cubes, otherwise it's very difficult.
Cool. Thanks.
Yeah, but I'm now more interested in doing this for general R here. So for this R here.
Are there some more questions to Hao? Well, if not, then let's thank him again. And then after that, I will stop the recording and we can have further chat.